Moltes gràcies, Jessica. Doncs ja per acabar les ponències d'aquesta jornada, a continuació el doctor David Fangueiro, de l'Instituto Superior d'Agronomia de la Universidade de Lisboa, ens parlarà de la modificació del pH com un tractament alternatiu per sanititzar les dejeccions animals. El doctor David Fangueiro és doctor en Química per la Universitat d'Aveiro a Portugal i l'Institut Nacional Agronòmic de França. És professor adjunt del Departament de Recursos Naturals, Medi Ambient i Territori de l'Institut Superior d'Agronomia de la Universitat de Lisboa i la investigació que du a terme es centra actualment en el reciclatge de nutrients i la gestió de fems animals, amb especial èmfasi en la influència del tractament d'aquests fems per separació i acidificació. Ha publicat 72 articles en revistes científiques, està involucrat en diversos projectes de la Unió Europea i és coordinador també de la xarxa Ramiran. So, David, when you want, you have 20 minutes, okay?
Okay, thank you. Thank you for the introduction. Thank you for the invitation to be there. And thank you for staying for this last one. I will try to be short and precise. First, I have to acknowledge my co-authors. The work I will show you has been done by a large team, so thanks to them. Quickly, a short introduction of the situation in Portugal. Maybe some of you are aware of this. So 3 main spots in terms of manure. Close to Lisbon. I hope everybody knows where Lisbon is, just for someone's there. So close to Lisbon, we have a large area of pig production. Then moving to the north, close to Porto, we have the dairy production. And a bit more to the east, we have the chicken poultry production. So we have 3 hotspots of manure production. In the north, close to Porto, for the dairy, it's not so much a problem because most of the manure is applied on the farms. For the chicken, it's not a problem neither because they export most of the compost, solid manure can be exported. And now we have the problem, the pigs producers. They don't know what to do with the manure. So we need to find some solutions. The easiest way is to go to the south. No, it's not what? Yeah, south of Portugal, where we have large areas. We produce lots of cereals. The soil is poor in organic matter content. But for this, we need to move the pigs, too many pigs to export them to the south. So what we started to see is what can we do in this region? And we identify something that the colleagues from Italy, the colleagues from Spain also identify. We have orchards, we have vineyards, and we have horticulture. So basically the idea is to find some new areas to apply this not problem. The pig manure is not a problem. It's a valuable material, so we need to use it efficiently. So the context, it has been said by many persons, so very quickly, too much manure, not enough space to apply it. We didn't mention it, but sometimes we have the area, but it's not anymore an area that can receive the slurry because we abused in the past. We applied too much, so now we have too much phosphorus, so we have to find a new one. Challenge, find some new areas. Our guess is that industrial horticulture and orchards are a good strategy. But before doing that, we need to ensure, as presented by some specialists, we need to ensure that it respects some standards. So it's sanitized. It has been said before, slurry, it's very good, many nutrients, many micronutrients, but there's also some specific microorganisms. I'm not a specialist as this. I will not say the names that are there. I'm not able to pronounce it, and not now, so I will not try. Something not so good, let's say that, but we need to live with it. So we look at what is the behavior of all these microorganisms with strange names. They don't like situations where the redox potential is not favorable. They don't like some high temperature, and they don't like some specific pHs. Playing with temperature and pH redox, it's not so easy. I will not heat the pH, I will not warm the pH, the slurry. So it's the 5 hours. So what we decide is to look at the effect of pH on the manure. Something important that we sometimes forget, and I was thinking about this when I heard some previous presentations. One easy way to hygienize is just to store the slurry and wait. Why? Because in aerobic conditions, some of these microorganisms are not so happy, and we will have one, let's say, hygienized product just by storing it. I will come back to this later. Another point is that when we apply the slurry to the soil, in some cases, the microorganisms may survive, but if we leave it, and now we start to have the conflicts with other interests. This morning we speak a lot about gas emissions. August also mentioned it this morning. The best solutions to minimize ammonia emissions, which one? Injection. When I inject, my slurry is not exposed to radiation. If the slurry is exposed to radiation, it's partially or totally sanitized. So we start to have this conflict of interest, and we need to find a solution that is good for gaseous emissions, but also for these questions. So, solutions for hygienization. Storage, the one I mentioned before. What is the main problem? In one farm, I don't have 10 slurry stores. I have one. And I have a continuous flow of manure in this store. So what is happening? I am continuously contaminating my hygienized pig slurry. Can I have 10 or 20 stores in my farm? Maybe not. So we will not use this solution. Anaerobic digestion, it works, but it's expensive. Sometimes if I was a farm, I'm not sure I will be able to manage this, so I need to rely on specialists. And in my point of view, one of the main limitations is that if I do co-digestion, I transform one product that is considered as organic fertilizer in a waste, and it can be a problem, but that's another stuff. Finally, UV and ozone treatment, so this nice machine, why not? But it's very expensive. So forget this. Thank you. So what do we need? Basically, we need something that is simple, low cost. We need to obtain something that can be used as a fertilizer. We cannot forget the fertilizing aspects of this product. We can promote some new applications, and we cannot forget the gaseous emissions, ammonia emissions, and the others, okay? So we need some simple solutions, but we need to consider all the problems that some new solutions can bring. So we will not follow the farmer that find a good solution to avoid gaseous emissions and avoid production of slurry. We will try to have a holistic approach. To do that, we set up a project, we get some money to do this project. Quickly, the concept of the project. We will play with the pH of the slurry. What I mean by playing, acidification, it has been mentioned this morning, but also increasing the pH. Why increasing the pH? The sludge from the waste treatment plant is treated by alkalinization, so it's not new. We will try to do the same with slurry. But if I do that, what happens? Ammonia emissions. So for that, what I need is to have a system that capture the ammonia that is emitted. But we cannot forget what the farmer asks. Simple solution. So to do that, I will not use any new product or any new machine. I use the residues from the crops that I produce. We test different crops. The residues from tomato are very good. We are happy with this. We did some, let's say, tuning on the tomato residue, and we improve the ammonia fixation. It reached close to 70% of ammonia recovery. So it works, it's simple, we can do that at the farm scale. Then we move on, we look at the impact of acidification and alkalinization on some indicators. We use E. coli and Salmonella to see if we consider that if it's efficient with these two, and I look at you because you are the specialist, maybe it's not enough, but we consider that if E. coli is affected by the treatments, probably the other ones are affected. But again, we need to look a bit more in deep later. So we look at the impact on pathogens, then we move, obviously, to the field. We apply it to the crops, different crops, tomato, salads, cabbage, potatoes, and we see if it has an impact on production. Here, I show you the different additives that we used to modify the pH of the slurry. For the acidification, I will start with the easiest one, this one. We use sulfuric acid. Why sulfuric acid? It's the most used one. It's cheap, so we consider this one. I will show you later some alternatives. What we show with sulfuric acid, that both in dairy and pig slurry, we can easily reach low pH values that should be able to, let's say, neutralize our E. coli. For the increase of pH, we select different additives, and here, as you can see on the graphs, to reach the higher target pH, 11, in some cases, we are not able to reach this. With urea, it's not possible. With ammonia, just we can reach it, but we need a large amount. So what are the candidates? Sodium hydroxide or potassium hydroxide? Obviously, we move to potassium hydroxide. Why? Because we are enriching the slurry with potassium. So we select this one, we move on with this, and we look at what is happening in terms of E. coli and Salmonella. In all the slurries that we used, we never detected Salmonella. So we forget this one, and we look at what happened with E. coli. On dairy slurry, as we can see, our raw slurry was quite contaminated. When we change the pH to pH 3.5, 4.5, 5, or 5.5, we have a strong decrease of the E. coli. The same when we increase the pH to 9.5, 10, or 11, we were below the legal limit. At 9, we also have an effect, but not so significant. When we move to pig slurry with a higher contamination in terms of E. coli, what we observed was that by decreasing the pH below pH 5 or to pH 5, we have a good effect. But at 5.5, as you can see in this graph, it's not enough. So we need to reach pH 5 to have an effect and have a situation that complies with the legal limit. When we increase the pH, the same, we need to reach pH 9.5 to have a nitrogenized slurry. Again, maybe my colleague will not agree. It's just regarding E. coli. So we didn't consider all the other parameters that has been pointed out. It's something that we are happy to to do with all of you, so it's an invitation to, to join us. But at this stage, I'm happy because with a simple treatment, pH modification, I have an effect. Just for the curiosity, if you want more details, you can have this on the paper. About acidification, we used in the previous study the sulfuric acid. If I was a farmer, I will not be happy to have a container of sulfuric acid in my farm. So what we did, and it's expensive. Even if now it's the cheapest one, it's still a cost. So what we did in this new project, we tried to find some alternatives to commercial sulfuric acid. And we identified some industries that use sulfuric acid and have a waste. That's what we call spent acid. And we use also ferric chloride. And again, what we observed is that we reach our target, we decrease below the detection limit the levels of E. coli. So even if we use something else than sulfuric acid, and now we are testing bioacidification, that is a promising treatment, we should be able to hygienize the slurry. Quickly, I will show you the results of one of the experiments we did in this project. Why this one? We did a study to assess the potential leaching after application of the different treated manures to the soil. So basically, we use a soil column inside a tube. We apply the slurry on the top, and then every weeks we simulate a heavy rainfall. We apply some water, and we collect the water at the bottom. And we analyze it in terms of nutrients, but also in terms of E. coli. So in terms of pH and conductivity, pH, why pH? Why looking at the pH? Most of the questions when we speak about pH modification is what will happen to my soil when I will apply the treated slurry? Will it impact the pH? And the truth is that after many applications of acidified slurry, we didn't observe a strong decrease of the pH. And the same, you can see on the graphs that the impact on the water that pass through the soil is not so different when we modify the pH of the slurry. We have a negative impact on electrical conductivity. Why? Obviously, we had sulfuric acid, we had potassium hydroxide, so we increase the amount of cations. It might be a problem with some crops, so it's something that we need to care. Quickly, the impact on nutrients. In terms of leaching, we observe when we acidified, we keep the ammonium inside the slurry, so a consequence is that we have an increased risk of potential leaching of this ammonium ion, but in terms of nitrate, that's okay. What we observed is something that is documented. We have a delay in nitrification, but nothing too much important. I move to the last one. In terms of leaching, what we use as indicator was the fecal coliforms. We need to have less than 100 units, and in all the leachates, even in the raw slurry, we never reached this value. The maximum was 25, and we observed a significant effect of our treatment. So we believe that it might be okay in terms of treatment. This pH modification seems to be, and I stress the point, seems to be, because we need to check many other points, a good solution for slurry sanitization. Concluding, saying just that all the solutions that we tested are okay to fight again E. coli. The application of this sanitized slurry in horticulture can be seen as a good alternative to mineral fertilizers. The tests we did in pots and in field conditions are promising, even if with some crops we had some problems. We burn some crops, it may happen, so we still need more work. This is the last point, and obviously we need to continue to work on this question to see how we can upscale this solution. Thank you for your attention, and I'm happy to answer some questions. Thank you.
Thank you, David. Pues, si hi ha una persona a la sala que té alguna pregunta, tenim temps per un parell de preguntes. Podeu passar el micròfon, sisplau? Si no, potser, igual te senten si parles. A veure, proveu. Vale, em diuen que no sentiran la traducció, perdó.
Bé, enhorabona a tots per les presentacions. Voldria fer una pregunta a la doctora Subirats. Ha mostrat els resultats del seguiment durant el procés de compostatge dels gens de resistència. En alguns la caiguda és immediata, diguem que decreixen en molts ordres de magnitud, no? En canvi, la resta, prou feines, arriba a un ordre de magnitud. Vull dir, del 100% baixa un 80%. Vull dir que no baixem un 1% o un 1 per 1.000. Bé, és igual. La fase termofílica sembla ser que és la part important. En digestió anaeròbia, teòricament, almenys pel que he llegit, pel fet que l'energia involucrada en el creixement és molt més baixa, el bacteri o les arquees tenen menys energia disponible per incorporar els plàsmids per transferència horitzontal. O sigui, hi ha més dificultat. Vull dir que teòricament tenen més dificultat en sistemes anaerobis que els gens de resistència realment es puguin transferir. Però no he trobat en digestió anaeròbia articles o treballs que puguin ser concloents fent mesures de si realment la baixada és molt forta. Però en les conclusions has posat que era interessant el compostatge i la digestió anaeròbia. Llavors la pregunta és, teniu dades concretes de realment, de la mateixa manera que teniu un compostatge de digestió anaeròbia, de fems, de purins, del que sigui?
La resposta és que no tenim aquestes... Perdó. Doncs la resposta és que no tenim aquestes dades mesurades durant el procés de la digestió anaeròbica i, de fet, el que posen en les conclusions és pel fet que en els resultats que he presentat, quan s'aplica el digestat al camp, sí que es veu que hi ha una reducció en l'abundància de gens de resistència quan ho comparem amb els altres tractaments, i d'aquí ve la conclusió una mica de que la digestió anaeròbica podria ser una bona estratègia per mitigar la resistència antibiòtica. Respecte al que dius de quin és l'efecte durant la... És a dir, si comparem els gens de resistència abans i després de la digestió anaeròbica, la veritat és que jo pels articles que he llegit és que depèn moltíssim de les condicions de la digestió anaeròbica, de les condicions, sobretot de si és un sistema tancat o és un sistema que es va alimentant contínuament amb purí. Perquè si és un sistema que es va alimentant contínuament amb purí, no es redueixen els gens de resistència molt. Això és la informació. No sé si et contesto a la pregunta. Sí. I de fet, una de les coses amb les que possiblement començaré a treballar, si tot funciona, és estudiar una mica la digestió anaeròbica en aquest aspecte, en la reducció dels gens de resistència.
Sí, una pregunta pel doctor Fangueiro. No m'ha quedat clar si la significació dels purins era sobre el purí sencer o sobre la fracció líquida de purí.
Sorry, I missed the first part of the question.
Sí, si l'acidificació la feien sobre el purí sencer, tal qual, o era sobre la fracció líquida del purí?
No, purí completo.
Purí entero.
Not liquid fraction. Correcto. We did some work on liquid fraction with acidification, and let's say that we need less acid, and the impact of acidification is more significant because we don't have let's say, the resistance of the solid fraction to acidification. So the impact of this treatment on liquid fraction, we believe that it should be more effective.
No, es que nuestra experiencia en acidificar purín porcino, acidificando fracción líquida, ¿me entiende? O sea, con 2 kilos de ácido sulfúrico, en fracción líquida es suficiente para bajar el pH hasta 5. Y este coste es perfectamente asumible, sobre todo en un momento en que el purín, valorándolo a precios de NPK comercial, un metro cúbico de purín puede valer más de 30 euros, con lo cual se puede asumir perfectamente el coste de la acidificación. Y con los resultados que usted ha dado, pues es muy interesante conocer estos resultados porque de alguna manera dan facilidad a que se pueda tratar la fracción líquida a unos costes perfectamente asumibles.
Okay, I'm not sure I get everything, but the question was about the amount of sulfuric acid we need to acidify the liquid fraction, right? Part of the question was this. So in terms of amount, for the, let's say, raw slurry, we need close to 6 liters per cubic meter to acidify to pH 5.5. So to reach pH 5, we need close to 7 liters. With the liquid fraction, the tests we did some years ago, we use close to 4.5 to 5 liters per cubic meter. Regarding the costs, something we need to consider is that the money spent for the acidification is recovered considering the amount of nitrogen that stays in the slurry. So if you had to compensate the nitrogen that is released by volatilization, and if you have to buy some mineral fertilizer to replace it, during this balance, you are saving some money. So even right now, with the increase of the prices of the sulfuric acid, not of the fertilizers, we still are balanced. So it can be seen as a let's say, balanced process. In terms of costs, it remains something of interest. If you can, again, if you give your slurry, you have a cost, definitely. If you can make some money with the export of the slurry, then you can, it's of interest. Did I answer?
Sí, correcto. Sí, okay.
Veient els resultats aquests que tens d'E. coli, com que trobeu, que detecteu E. coli en mostres una mica random, que no teniu... Jo pensava que podria ser, que no sé si us heu plantejat que podria haver contaminació al laboratori, que realment no. Ah, sí, perdó.
I una vegada aquestes mostres nosaltres les enviem al laboratori perquè analitzin i ens donguin el resultat, aquí ens perdem. Jo suposo...
Perdona, que em pensava que ho feu al vostre laboratori.
No.
Faig un petit comentari jo, perquè amb ell hem parlat largo i tendido sobre aquest tema de les contaminacions així una mica més random i clar, ho ha parlat també de l'EFSA. La font de contaminació no és únicament l'eslurri. Tu pots tindre contaminació per un animal salvatge, per l'aigua, per un ocell, llavors, pot ser, alguna vegada hem parlat en el cas de les fulles que hi hagués un pardal que s'hagués quedat a les fulles, vull dir que la font no és únicament no és únicament l'eslurri que tu tens allí, el que dèiem dels manipuladors, hi ha moltes fonts de contaminació dintre d'una finca que poden afectar a que hi hagi presència. Per això també inclús havíem parlat de traçar si les soques són les mateixes que hi ha al purí a les soques que es troben. Llavors, aquí hi ha molt camí per explorar. Alguna pregunta més? Bé, doncs donem per finalitzat aquest bloc i, Carlos, si vols...
Sí, si voleu, moltes gràcies. Si voleu, no cal ni que us mogueu, perquè com que anem super amb temps, doncs ho farem més ràpid. Moltíssimes gràcies en aquest últim bloc. Jèssica, Josep Maria, David, Josep, Gemma i Maribel, per la moderació també. Molt breu, acabem la segona edició de PROFEM, contents per acabar l'hora i també sobretot pels assistents, 140 el primer dia, de l'ordre de 120 aquest segon dia. Jo crec que és una dada prou bona. De l'ordre de 40 entre ponents i moderadors han passat aquests dies, aquests 2 dies. És una xifra considerable per organitzar i per moure. I també agrair, evidentment, amb ells, i agrair també els socis del projecte, el CSIC, ERSAF, de Llombardia, IRTA, d'ISAFA, de la Universitat de Torí, amb un projecte cofinançat per la Unió Europea, i evidentment el Departament d'Acció Climàtica, l'Oficina de Fertilització i el Servei de Sols i tots els participants i que han fet possible que poguéssim fer aquesta jornada. I bé, simplement dir-vos que les ponències les penjarem a la web de l'Oficina de Fertilització, amb uns resums que també hem demanat als ponents que anessin fent per tindre una mica de la prosa, una mica el seguiment d'aquest fil conductor que han fet a les xerrades. I, no ho sé, emplaçar-vos, suposo, d'aquí 2 anys amb una tercera edició, no sé on, ja ho decidirem, i sobre quina temàtica més específica, potser marcat amb algun altre projecte, no ho sé. Ho veurem, us informarem i rebreu la informació també quan tinguem les ponències penjades, us ho enviarem. D'acord? Moltes gràcies per haver resistit fins aquí, els que esteu aquí presents. Merci a tothom.
can your love do for me? When will love be through with me? Why live life from dream to dream and dream the day when dreaming ends? your love to yesterday.